Moving right along through the material, let's look at Chapter 4, Polynomial and Rational Functions. In this chapter, we'll graph polynomials to the best of our ability, restricted to algebraic manipulations. We'll be moderately successful, but really to graph polynomial functions, you need a little bit of Calculus 1. But we'll get quite a bit done with our limited tools of Precalculus 1. You'll have a complete toolbox with that analogy in Calculus 1. And we'll also look at rational functions and horizontal and vertical asymptotes of rational functions, and we'll do our best to graph rational functions as well. And at the end of this chapter is some commentary about the fundamental theorem of algebra, something that'll require a brief exploration of complex numbers. But section 4.1, polynomial functions and models. The plan here is to graph. So we're going to consider polynomial functions by definition, their degree, and graph them and analyze the graph of a polynomial. So the big picture is we want to graph polynomials as best we can with the equipment of Precalculus 1. First, a polynomial function in one variable is a function of the following form. F of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, and so forth, down to a sub 2x squared plus a sub 1x plus a constant a sub 0. All the a subscripted a's are constants. They're called coefficients. N is required to be a non-negative integer. It's debatable as to whether or not we would consider constant a polynomial. There's some settings where it is and some settings where it isn't. We're allowing n to equal 0, giving us a 0-degree polynomial, which I'm okay with, provided we don't have the polynomial f of x equals 0, the 0 function. That it's unlikely we'll want to count as a polynomial. Constants may be constant functions, but not the constant 0 in particular. We'll require a sub n to be non-zero, this leading coefficient. We're saying this is an n-degree polynomial, so we want to make sure it actually involves an x to the n term. So that's why there's the restriction that a sub n be non-zero. The monomials that sum to give this polynomial function are the terms. So the monomials are just the single little pieces like that, constant times power of x. So these are the terms of the polynomial. And when the polynomial is written in this form, it's said to be in standard form. That is, decreasing powers of x is how this is written. So let's look at a couple of quick examples. Okay. Determine which of the functions are polynomial functions. For those that are, state the degree. For those that are not, tell why not. Write each one in standard form. All right, so h of x equals square root of x times square root of x minus 1. Is that a polynomial? Remember, polynomials have non-negative integer powers of x. X to the 1/2 is going to be a problem here. Let's go ahead and multiply out. If we take square root of x times square root of x minus 1, quantity, square root of x times square root of x minus the square root of x upon distribution, square root of x times square root of x is x itself. Of course, there's a restriction that x be non-negative because we can't take the square roots of negatives. This is not a polynomial function because of the square root of x, which is the same as x to the 1/2. Polynomial functions are of the form a sub n, x to the n, blah, 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 constant times x plus a sub 0. There is no x to the 1/2 in a polynomial, so not a polynomial function. So we can't address these other things that they've asked about in number 24. No fractional powers of x in a polynomial. No negative powers of x in a polynomial. Only non-negative integer powers of x in a polynomial. Number 28. Let's multiply out. G of x is negative 3x squared times x plus 2 cubed. Okay, x plus 2 cubed, it'll be a little bit of a mess to multiply out. We had a formula for it, I think, in the appendices. Maybe we'll just take it in smaller steps. Let's take the given polynomial. Let's write x plus 2 cubed is x plus 2 times x plus 2 squared. Foil this, or remember the formula for squaring a binomial, and then we'll distribute the x plus 2. X plus 2 quantity squared, square of the first, twice the product, square of the second. That's what FOIL produces. So we get x squared plus 4x plus 4. Feel free to pause and double check all that algebra. Now we need to distribute the x plus 2 on this. So we'll have x plus 2 times x squared. Well, how about this? X times, let's distribute the x first and the 2 second. I think that's how it's written out here. So we'll have x times x squared is x cubed. X times 4x is 4x squared. X times 4 is 4x. Now the plus 2 part. Take the 2, distribute it across this, will produce a positive 2x squared plus 8x plus 8. And there are those terms. Let's collect those together in common powers of x, kind of a standard form of the polynomial related, relevant here. There's a single x cubed term. There's a 4x squared and 2x squared. There's a total of 6x squares in the parentheses, a total of 12 x's in the plus 8. So here's that stuff in the parentheses. Let's go ahead and distribute the negative 3x squared and put it in standard form. Distributing, we'll have adding exponents, negative 3x to the 5th, right? Negative 18x to the 4th, adding exponents. Negative 36x cubed, right? Adding exponents. And negative 24x squared. So here we have the polynomial. Actually, it really is a polynomial. It's in the right form. And we've got it in standard form as given here. So G really is a polynomial. It's a sum of constant multiples of powers of x, where those exponents are non-negative integers. So it is a polynomial function. Its degree, the highest power of x, is 5, so it's degree 5. The leading term, the term involving the highest power of x, is this term here, negative 3x to the 5th. And the constant term, they ask about these things as well. The constant term is 0. There's no constant added over on the side, or the constant 0 is added on the side. The coefficient of x is also 0 because there's no x term. All right, so let's see. They did ask for the polynomial in standard form, and here it is in standard form. So I probably should put that in a box as well. Back to the notes. In calculus, you'll define what it means for a function to be continuous and smooth. Here we're going to approach it fairly informally. This is done in Calculus 1. Section 2.5, you'll cover continuity. It's defined in terms of limits, so it's off the table for us. Smooth is defined in terms of something called derivatives, so also off the table for us. That's actually done in Calculus 2 in a section on arc length. The term smooth is defined and has a formal definition in terms of derivatives. All polynomial functions, it turns out, are smooth and continuous. For us, that is in here, by smooth, we mean that the graph contains no sharp corners or cusps. By continuous, we mean that the graph has no gaps or holes and can be drawn without lifting your pencil from the paper. This bugs me because that's not what these ideas are in any rigorous way. It's all we've got, so that's the way we'll have to approach it. It's informal and intuitive, but we'll muddle through with that. In Calculus 1 and Calculus 2, you'll formally define these things using calculus. So here's a graph, maybe, of some polynomial function. Is smooth everywhere, and it's continuous. I can draw it without picking up my pencil. There's no sharp points, no holes in it either. Here's a graph that's not a polynomial function. It's got a corner in it, as they call it there, a little sharp point, a cusp, another kind of sharp point. It's got a gap in it there. I couldn't draw it without picking up my pencil right there. I'd have to pick up the pencil. I got a hole in it here, another place where I'd have to pick up my pencil. So these corners, cusps, and the little holes or gaps in the curve, messing up the continuity, say this ain't a polynomial function. Polynomial functions won't have holes or gaps or cusps or corners, sharp points in the graph. That's why they call them smooth, no sharp points. So there's an informal idea of what we're up to in terms of polynomial functions. A simple power function of degree n is a special polynomial function. It is a monomial function of the form f of x equals ax to the n. A is a real number, not zero, and n is a positive integer here. So we're requiring n be greater than or equal to 1, strictly greater than 1, and an integer. Power functions will play a role in something called n behavior that we'll address here in a little while. We're going to look at some power functions and add them to the library of functions. We're going to consider power functions where this a parameter is 1 in the following conversation. First off, you're familiar with the graph of y equals x squared. In section 2.4, we put it in the library of functions. So we're going to compare that to the power function f of x equals x to the n, where n is even. We'll consider n odd next, but first, we're comparing y equals x squared and really y equals x to the n, where n is even. The claim is a power function f of x equals x to the n, where n is even, has a similar shape as the graph of y equals x squared. I think I'm quoting from Sullivan's text and so a lot of this verbiage. The shape of y equals x squared was a parabola. These other functions, they don't have graphs that are parabolas. They have graphs that kind of look like parabolas, but strictly speaking, they're not parabolic shapes. Parabolas have certain properties, and the graphs of these functions don't share those properties. You graph y equals x to the n, where n is even and greater than 2. You're not getting a parabola, you're getting something else. But at least it has the opening upwards type behavior, as we'll illustrate with some pictures. Some additional properties, actually, let's look at a picture first. So here in black is the graph of y equals x squared. Here in blue is the graph of y equals x to the n, f of x equals x to the n, where n is even and greater than or equal to 4. Trust me on that. That's how we're building this library of functions, kind of trusting that the shapes are as the book has claimed. And let's zoom in a little bit on this. All right, in blue, it opens upward, just like a opening upward parabola does, just like the graph of y equals x squared does. So in that sense, they're similar in shape, whatever similar means. Also, what's happening between x equals -1 and x equals +1 is the f of x equals x to the n function, where n is greater than 2 and even, that is n is greater than or equal to 4 and an integer. The points on the blue curve are closer to y equals 0 than the points on the black curve. I mean, if you think about it, somewhere over here is 1/2. If we take 1/2 squared, we get 1/4. But if we take 1/2 to the 4th power, we get 1/16, which is a lot smaller. So when you take these numbers between -1 and 1, such as 1/2 or -1/2, I guess I was indicating there, but you take a number between -1 and 1, you raise it to an even power, it'll be positive. There's symmetries we can observe from these. But when you raise a number that's less than 1 to a high power, it gets really small. So what's happening here is between -1 and 1, the higher power of x will produce a curve that's closer to the x-axis, closer to the line y equals 0, closer to an output of 0. But if you choose a number bigger than 1, you raise it to a higher power, you get out a bigger y value. For example, when we plug 2 into y equals x squared, so I follow it correctly, we get out 4. When you plug 2 into this function, you get out, I don't know, something much bigger. If this is x to the 4th, we get 2 to the 4th, which is 16 out. So that wouldn't even fit on the screen. But what we're getting out then is bigger values from x to the n, where n is greater than or equal to 4, when we put in numbers bigger than 1. And similarly, numbers less than -1. These numbers over here, they're bigger than 1 in magnitude. Take the absolute value. But when we raise these to an even power, of course, we only get non-negative things out, and you take numbers bigger than 1 in magnitude, that would be x values greater than 1 or x values less than -1. And you're going to get larger things out, greater things out of the x to the n function than you do out of the x squared function. And that certainly makes sense. If I just look at this little part over here, let's take x greater than 1. 3 squared is 9. 3 to the 4th power is 81. So we're getting lots bigger numbers out on the blue function than we are on the black function. For example, if I considered n equals 4. So that's what we're going to describe in the previous paragraph. We're going to describe these points are closer to the x-axis on the blue curve than they are on the black curve. And these points on the blue curve are further from the x-axis than the corresponding points on the black curve. So here's how it's stated in the previous note. For x between -1 and 1, -1 less than x less than 1, and x not equal to 0, the points on the graph of f of x equals x to the n, where n is greater than or equal to 4, are closer to the x-axis, than the corresponding points on the parabola y equals x squared. So the properties we're being told are similar shape, but for x values between -1 and 1, we get corresponding points closer to the x-axis. For x less than -1 or greater than 1, this is all the other x values except for 1 and -1, the points on the graph of f of x equals x to the n are farther from the x-axis than the corresponding points on y equals x squared. That's what we just illustrated. Not only that, the bigger n is, the farther these are from the x-axis, and the closer the others are to the x-axis for various input values. That's also illustrated in the figure below. Here, they're comparing x to the 4th and x to the 8th. So we magnify quite a bit because we're looking for some pretty subtle details here. So this is x to the 4th. Here in black, you have what was drawn maybe in blue on the left-hand side. Here in black on the left-hand side, we had y equals x squared. Over here, we've got y equals x to the 4th. This is a different shape from the black curve over here, right? It's the same scale. Yeah, it's pretty subtle. The sides here, they're steeper. It's steeper, say on this right-hand side of y equals x to the 4th, than it is on this right-hand side of y equals x squared. So that's one little difference that I think I can see. And there's a mirror image difference on the left-hand side. What's happening between -1 and 1, there's also some differences there, but it's quite subtle. But here they've graphed y equals x to the 4th and y equals x to the 8th. Well, in the picture, it almost looks like these go vertical. They do not go vertical because this is a function. Can't violate the vertical line test. But when you raise numbers to the 8th power, you get really, really big numbers out pretty fast. That is for small x values. I plug 2 into here, we get out 2 to the 8th power. That's what, 128, I think. So that's a huge number on this scale. I mean, there's 4 units there, so we want some 128, something much bigger than this. on this scale. But these do not go vertical because we're dealing with a function. They just grow really, really rapidly. And what you see comparing x to the fourth to x to the eighth is between -1 and 1, the blue points are closer to the x-axis than the corresponding black points. Greater than 1 and less than -1, the blue points are further from the x-axis than the corresponding black points. And it's hard to find corresponding points because this one grows so quickly. But how about over here, right, where the arrowhead is? If I trace that straight down very subtly, we're putting in a number a little bit bigger than 1 and producing this value here. The corresponding point on the black curve might be this point here. So I'm comparing this point and say the point at the arrowhead there. Yeah, these are corresponding points. They have the same x values, if I'm really careful, but their y values are quite different. We get a relatively small y value out of x to the fourth and a relatively large y value out of x to the eighth, y equals x to the eighth. So here you're seeing bigger exponents yield more extreme versions of this closer to the x-axis and further from the x-axis stuff described on the left. If we were to graph y equals x to the, who's next? They did 4 and then 8. We want, just want even. I guess we look at x to the 10th. I don't know why they didn't do x to the 6th, but whatever. If we look at x to the 10th, even exponent bigger than 8. If we were to graph that, probably couldn't quite tell the difference. We'd see it steeper still coming through this point and closer still to the x-axis in corresponding positions. So that's the kind of behavior we would see. This even more extreme, and it probably on this scale, probably virtually impossible to see that in a graph. But these are some of the subtle behaviors that you need to know, because the graphs are probably not going to illustrate those very well. You generate these with software, probably going to have trouble distinguishing between some of those graphs if we make the exponent really big. Some properties of f of x equals x to the n, where n is a positive even integer. So we're considering evenness still. Like I said, the odd is to follow. F is an even function. Yeah, if you got x to the n, where n is an even positive exponent, negative signs will be absorbed. We'll have an even function. That is, we'll have a function whose graph is symmetric with respect to the y-axis. Both of these, symmetric with respect to the y-axis. All of these. The domain is a set of all real numbers. The range is a set of all non-negative real numbers. Yeah, any real number can be raised to the nth power where n is a positive even integer. What you will get out will be non-negative, and you can get all non-negative numbers out. Maybe I take my inspiration from that second claim by saying, yeah, look at the graphs. They open upwards. They, you could talk about minimums. They have a minimum of 0, an absolute minimum. They don't have an absolute maximum. And they take on all values, all y values greater than 0. Property 3, the graph contains the points -1, 1, 0, 0, and 1, 1. If we go back and look at the graphs of all of these, they all pass through the origin, the point 0, 0. You plug 1 in, you get 1 to the n power out. Well, it's going to be 1, and that's going to hold, passes through the origin, and the point 1, 1, that holds for all of these. You plug -1 in, you raise -1 to the nth power, where n is even, and that'll yield +1 as well. If n is odd, it's a different story. But with n even, you plug -1 in for x, and you get +1 out for y, because n is even. Negative sign is absorbed. So all of these graphs of power functions where n is even pass through those 3 points. As the exponent increases in magnitude, the graph is steeper when x is less than -1 or x is greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. That's the book's way of describing this closer to the x-axis stuff here, and the super steepness here to the right. This is super steep, and to the left, super steep. So we'll consider that properties that we accept for power functions of the form f of x equals x to the n, where n is even. And we took a lot of inspiration on this from the squaring function, f of x equals x squared. Let's turn our attention to n is odd and take our inspiration from x cubed. You're familiar with a graph of y equals x cubed, hyperlinked there in the notes online. We introduced this in section 2.4, and we drew a graph of y equals x cubed by plotting a handful of points. And we accepted that the shape the book gave us was the actual shape of y equals x cubed, taking that in the library of functions, and we did translations of these. We'll translate these power functions here shortly as well. A power function, f of x equals x to the n, where this time n is odd, so we're considering now odd exponents, is closer to the x-axis than the graph of y equals x cubed for x between -1 and 1, and farther from the x-axis than corresponding points on y equals x cubed for x less than 1 or x greater than 1. This is the same thing we had before in terms of closer or further away. Now, which direction it goes in is going to be a little bit different in this story, but the closeness and the furtherness, those ideas still hold and still hold in the same place. Here we're looking at, in black, the graph of y equals x cubed, and in blue, the graph of y equals x to the n, where n is some exponent greater than or equal to 5. If this was graphed with software, I suspect n equals 5, or else it'd be really hard to see what's happening with these. And what you see is between -1 and 1, over here on the right-hand side, these look a lot like the pictures we had above. The blue stuff is closer to the x-axis than the black stuff, corresponding points. Now, the same thing's happening over here. The blue stuff is closer to the x-axis than the corresponding points on the black curve, but that closeness puts the blue ones above the black ones over here, and the blue ones below the black ones over here in corresponding positions, but still closer. We still have that idea. We take a point somewhere around here for an x value. The blue graph has a point here that's closer to the x-axis than the corresponding x value produces for a point on the black curve, the y equals x cubed curve, closer to the x-axis. Beyond this, we get further. The blue curve is further from the x-axis than is the black curve, and that holds over here as well, even though the curve is going even though we're below the x-axis. I choose my words carefully over here. Below the x-axis, we've got the same kind of behavior in terms of closeness to the x-axis. And here we're looking at x to the 5th versus x to the 9th, and same behavior. So we'll say something like that closeness holds. Not only that, the bigger n is, the more this closeness holds. If we made n odd and really, really big, I'd expect to see a curve that's super duper steep, and it goes rushing towards the x-axis and levels off. And it's almost level, but not quite. It passed through the point 0, 0. It'd stay really close to the x-axis, then it'd take off and pass through this point and be super steep. So that's the behavior of x to the n when n is an odd positive integer. So some properties of power functions of the form f of x equals x to the n when n is positive, odd integer. We got an odd function, so it has symmetry with respect to the origin. These all had that kind of symmetry. With respect to the origin, I go over and up, and I find a point on the curve. If I went back and down, same amounts, I'd find a corresponding point. The arrowheads correspond on the cubing function, for example. The domain and range is a set of all real numbers. Yeah, any real number can be raised to the nth power. You can plug it into the function f of x equals x to the n, where n is a positive odd integer. And looking at the graphs, remember it's hard to find ranges unless you have a graph. Now we do. The range is all real numbers. All y values come out of these functions, just like with the cubing function as discussed in a previous section. The graph always contains the points -1, 0, 0, and 1, 1. Right, similar to what we had above. Put 0 in, get 0 to the n out. So we get 0, 0, 1, comma 1 to the n. Going to produce 1. -1, comma -1 to the n. When n's odd, that's going to be -1. If n were even, we had +1 out. We had a point up here. So for x to the n, when n is odd, we get the curve to pass through these 3 points. Notice they all pass through those 3 points. And then they have that steepness behavior and closeness to the x-axis behavior around those points. As the exponent n increases in magnitude, the graph is steeper when x is less than -1 or greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis, as I tried to describe. So we get graphs that look something like this when n is odd. Let's look at number 38. Okay, they got us graphing this function. It says use transformations of the graph of y equals x to the 4th to graph f of x equals x plus 2 to the 4th power minus 3. Okay, we have added to our library of functions x to the 4th, in fact x to the n, where n is any integer, non-negative integer. We'll start with y equals x to the 4th. I'll do this on the next slide and see the graph. We're trying to take this library of functions graph and produce this thing. Well, first, let's get the +2 in there. We'll do so by replacing x with x minus -2. You remember, we want to think in terms of these substitutions as we did when we dealt with transformations in the past. That is x plus 2, but we want to write it as x minus -2. The negative on the -2 will indicate which direction we're shifting things. We're shifting things to the left by 2 units, as it says down here. But make that substitution, and then that will produce, substituting for x in this graph, x plus 2, that will produce y equals x plus 2 to the 4th power. Not there yet, but closer. This is a horizontal shift of y equals x to the 4th to the left by 2 units. Why left? Because we've used a negative here. And be careful, review the transformation stuff if necessary. It was always x minus something. It was the type of substitution we made. When the something was negative, we shifted to the left. When the something was positive, we shifted to the right. So this is a shifting to the left by 2 units of the graph of y equals x to the 4th. Okay, we still need to get the -3 stuff, so we'll subtract 3 from that. We subtracted 3 from the graph. This is equivalent to a vertical shift down because we subtracted 3 because of the negative. So a shift downward by 3 units of the previous graph. So the desired graph results from taking the library of functions y equals x to the 4th graph and doing 2 things. First, a horizontal shift to the left by 2 units, and then a vertical shift down by 3 units. So in blue, we have a graph of y equals x to the 4th. First, shift it to the left by 2 units. So we'll take this 0, 0 point, shift it over here to get the point -2, 0, 2 units to the left, and then take the resulting green graph, which is, this is the formula for that function, and shift it down 3 units. So the vertex comes down to here. Any other target points, key points, I think it was, the book called it when we were doing transformations. X to the fourth, so 4 is even. We've also got this point 1 1 and this point -1 1, and notice they got shifted over and down as well. For example, the point 1 1 translated to the left 2 units and down 3 units. Here's the corresponding point. By the way, it's the point -1 -2. This point -1 -1 moved over 2 and down 3 to produce this point. That's the point what? -3, -2, which simply is 1 unit to the left and up from this lowest point, as is the key point on the original graph. So there's what the graph of y equals x plus 4 quantity to the 4th power -3 looks like. That's pretty good just for using precalculus. We could also deal with expansions and contractions. That was when we'd have a coefficient in front of the x term over here, or in front of the x term itself, maybe inside. And those were always more difficult to reflect. The translations are easy to express. When we have the expansions and contractions, it maybe opens these up more or makes them open up less. And that's a little bit harder to reflect. So I prefer the transformation questions. Back to the notes. So there's how we can use transformations and this new collection of functions in the library of functions to graph even more stuff. Okay, we want to kind of shift over to a more general exploration of polynomials than just these powers of x functions. Figure 2 here shows the graph of a polynomial function with 4 x-intercepts. It crosses the x-axis here and here and here, and it touches the x-axis here. So we need an algebraic way to decipher that. At the x-intercepts, the graph must either cross the x-axis or touch it. Consequently, between consecutive x-intercepts, the graph is either above the x-axis or below the x-axis. So here's what that means. If we know these are 2 points, consecutive points, where the graph of the function touches or crosses the x-axis, that is 2 consecutive x-intercepts, then we know that either, this is only given that information, if we didn't have the graph, we'd know either that function is above the x-axis between those 2, or we would know the function is below the x-axis between those 2. If all I knew was these were consecutive x-intercepts, I could deduce it's either above the x-axis between those 2 intercepts, or it's below the x-axis between those 2 intercepts. It couldn't be above part of the time and below another part of the time without crossing the x-axis again. If we can find all these x-intercepts, and we can by factoring, then that gives us some idea of what the graph must look like. It must be above or below the x-axis between consecutive x-intercepts. If this is the first x-intercept when reading from left to right, then that graph must be entirely below the x-axis as drawn, or possibly entirely above the x-axis as drawn. Can you find a function with the same intercepts that's not this one? Yeah, just reflect what you're given about the x-axis. Then you'd have a curve that's positive above the x-axis, then below the x-axis, then above, and then above some more, and then below. So only knowing the intercepts isn't nearly enough information, but it tells me something about the behaviors. I know that graph has to be entirely above the x-axis between consecutive intercepts, or below the x-axis between consecutive intercepts. It's an interesting little behavior here. It's below the x-axis, goes back and touches it, and then it stays below the x-axis. Yeah, that's because it touches the x-axis instead of crossing the x-axis. And that counts as an x-intercept. Touches the x-axis is probably not a term you'll hear in calculus, but it's a term that Sullivan, the textbook authors, used repeatedly when we've looked at graphs of functions. If f is a function and r is a real number such that f of r equals 0, then r is called a real zero of function f. If f is a polynomial function, a real zero is sometimes called a real root. So you might speak of roots of polynomials or zeros of polynomials. In general, you don't speak of roots of functions unless they're polynomial functions, or at least algebraic functions. But that's standard terminology. We'll use the words root and zero interchangeably, probably in Precalculus 1. It becomes a little bit more complicated in Precalculus 2 when you introduce all those trig functions. All right, so the roots of this polynomial function are this x value, this x value, this x value, and this x value. Has 4 roots because it touches or crosses the x-axis 4 times. An intercept corresponds to a root or a zero of the function. Let's look at a couple of examples. Okay. They have us creating a polynomial function whose real zeros are -4, 0, and 2, and whose degree is 3. Answers will vary depending on the choice of the leading coefficient. All right. Let's try to decipher what that last little part means as well. All right. Okay, they want -4, 0, and 2 to be zeros of this polynomial function. Well, if you want -4 to be a zero of that polynomial function, let's make x minus -4, that is x plus 4, a factor of that polynomial function. Why do you want to factor polynomials? Probably to find the roots of those polynomials. So factoring into linear terms of this form, and finding roots is the same puzzle. You want -4 to be a root of the polynomial function, make x plus 4 a factor. Then when you plug -4 into that factor, you'll get 0 out, and 0 times the other factors will produce 0. You want 0 to be a root, then we'll make x minus 0 a factor, or just x itself. You want 2 to be a factor, 2 to be a 0, then we'll make x minus 2 a factor. So if we have the factors x plus 4, x, and x minus 2, this multiplied out, trust me on this, foil it, foil these two, and then distribute the x. Maybe it's the easiest way, but you'll produce this. This third degree polynomial, they wanted a third degree polynomial, will have the desired zeros because it can be factored as this, and that's where it came from. So -4 is a root, right, because this term will be 0 at -4. 0 is a root, yeah, because if x equals 0, this product will equal 0. X equals 2 is a root or a 0, yeah, because if we plug in x equals 2, then this is 0 and the product is 0. So this is a third degree polynomial with the roots -4, 0, and 2. So we could take this, let's take this as the answer. It's the right degree and it's got the right roots. Now about this, answers will vary depending on the choice of the leading coefficient. What you could do is you could take this and multiply the whole thing by, I don't know, 7. If you put a 7 in front, of course that cascades through and each of these get affected by that 7 upon distributing. But if you had 7 times this product, it's still got the same 3 zeros. So there's another answer. So that's the idea of answers will vary. Had we multiplied this by 7 or -4 or whatever, non-zero, that would produce another third degree polynomial that has the same roots. So this is the easiest one because we've multiplied by 1 in a sense. We've got a leading coefficient of 1. So those are usually the easiest ones. So you can multiply by non-zero constants this function, and that would produce some other correct answers. But this is the natural correct answer. It's the easiest one. Okay, so there they gave us the zeros and the degree, and we found a polynomial. In fact, we found arguably a family of polynomials. In number 52, they do a similar thing, but they give you an additional piece of information. Find the polynomial function of degree 3 with zeros -2, 0, and 2, and whose graph passes through the point -4, 16. So this is new stuff here. All right, we'll start it the same way we did the previous one. You want roots at -2, 0, and 2. Then we'll take as factors x minus -2, that is x plus 2, x minus 0, that is x, and x minus 2, and multiply those three together. It'll have a root of -2 because that makes this 0. It'll have a root of 0 because this term then will be 0. It'll have a root of +2 because then this factor will be 0. Multiply out, maybe multiply the two binomials together. That'll give x squared minus 4, and then distribute the x to produce this. Here's a third degree polynomial that has exactly these three roots. So there won't be any other factors, or else you put more factors in, you change the degree. That was commented in the previous one as well. But we're not done with this one because they wanted this other stuff. Remember, I could take this and multiply it by any constant I want. How about we multiply it by constant a? Let's take f of x equals a times x cubed minus 4x. The x cubed minus 4x factors into the product of these three things. So it's still got the same roots. So we're good there. But we also wanted the function to pass through the point -4, 16. So that's why we put the a out front. Here's all possible answers. Like I said in the previous one, maybe we found a family of solutions. Here, we're going to get a unique solution. We've got something you might encounter in future mathematical contexts as like an initial condition, this might be called. Anyhow, we want the graph to pass through the point -4, 16. So let's plug -4 into the function. Let's take f of -4. We want that to equal 16 because we want the function to pass through this point. Plugging -4 into the function with this unknown coefficient a gives us -4 cubed minus 4 times -4. Trust me on the arithmetic. We'll get -48 times a, and we want that to equal 16. All right, so here's what you get from the function by plugging in -4, and you want that to equal 16. Set it equal to 16, and here's an equation you can solve for a. Divide both sides by -48, and we get a equals 16 over -48, or -16 over 48. That simplifies to -1/3. So we must have a equals -1/3. And the function must be f of x equals -1/3, quantity x cubed minus 4x. Does it have the right zeros? Yeah, this will factor into that, giving you the correct desired zeros. They wanted third degree. Okay, we got the highest power of x is 3, so it's a third degree polynomial. And they wanted it to pass through -4, 16. If the arithmetic here is correct, you plug in -4, you'll get 16 out as desired. So this is similar to the previous one, except in the previous one, we never really found that leading coefficient, or we set it equal to 1 because they just wanted an example of a function. Here, if they hadn't mentioned a thing about the point, I could have given the answer simply as this. X cubed minus 4x is a third degree polynomial that has these three roots. But this, bet you, doesn't contain that point, which is why we had to introduce the leading coefficient as something arbitrary and determine that from this extra information. Let's go back to the notes. And a definition of the multiplicity of a factor. If x minus r to the m is a factor of a polynomial f, and x minus r to the m plus 1 is not a factor of f, then r is a zero of multiplicity m of the function. So m is the exponent on the x minus r. Now, when you factor it, you collect all those common factors together. What all this stuff here means is x minus z to the m power. M is the biggest exponent you can put on x minus r when you factored it. That is x minus r to the m plus 1. There's not that many factors of x minus r in the factoring. So this defines multiplicity of, it's actually multiplicity of a zero. I might refer to it as the degree of the factor or something like that as well. We're going somewhere with this zeros of various multiplicities, and this will arise when we do the fundamental theorem of algebra at the end of this chapter. Number 56, as an example, says, find the polynomial function of degree 5 with zeros, -1 with multiplicity 2, 0 with multiplicity 1, and 3 with multiplicity 2, and whose graph passes through this point. Okay, this is copied verbatim out of the textbook. Let me elaborate a little bit. So they're saying -1 is a zero of multiplicity 2. 3 is a zero also of multiplicity 2. 2 more. And 0, they didn't write this clearly, but 0 is a 0. 0 is a root of multiplicity 1. So there's the 5 in the degree 5. So it's a bit ambiguous how they've stated this, but that's what they're intending to mean. So we want a polynomial function that has roots, -1 of multiplicity 2, 0 of multiplicity 1, and 3 of multiplicity 2. So -1 is a root, we'll need x minus -1 as a factor. That is, x plus 1 we'll need as a factor. Ooh, of multiplicity 2, so we'll need x plus 1 to the second power. M equals 2 in this case. So x plus 1 squared will give the root -1 of the polynomial function that we're looking for, and it will be multiplicity 2 because there will be an exponent of 2 on that factor. 0. Okay, we'll take x minus 0, or simply x as a factor. It's understood they mean of multiplicity 1 here. So this we treat just like we did in the previous examples. And 3, a 0 of multiplicity 2. So we'll take x minus 3 as a factor to the second power because it's of desired multiplicity 2. So if we'll multiply these factors together with the appropriate multiplicities, appropriate exponents, we get x plus 1 squared times x minus 3 squared. This must be a factor of the desired function f. They also said f is of degree 5. Well, if you'll multiply this out, we'll pick up an x squared here, an x here, and another x squared here. Multiply all those x's together. That'll give you x to the 5th. Multiply this out, and you do indeed get a 5th degree polynomial. They didn't ask for standard form or anything. If they did, we'd do the actual multiplying out. It'd be a little bit tedious. It wouldn't be that enlightening. The important thing is this is a 5th degree polynomial. So there can't be any other factors involving x of this function f. If there was another x minus something, then you'd have a 6th degree polynomial. And we know we're looking for a 5th degree polynomial. So the desired function f, the polynomial function, must be some constant multiple of what we have up here. Let's rewrite it a little bit and bring the x factor to the front. X times x plus 1 squared times x minus 3 squared. Some non-zero constant multiple of that. F of x must be of the form a times x plus 1 squared, x minus 3 squared, just like in the previous example, except this time we got those exponents on there. How do you find a? Well, just like we did in the last one. We know f of 1 must equal negative 48 because we want the point 1, negative 48 to be on the graph of function f. What does that mean? F of 1 equals negative 48 when x equals 1, f of x equals negative 48. So that's the information we're desiring to satisfy. And we know f of x in terms of x and this unknown parameter a. And we'll find a using this information. F of 1 is, plugging 1 into the function, would be a times 1 times 1 plus 1 squared times 1 minus 3. Quantity squared, which is exactly what's written here. The ones in parentheses are the ones I put into the function. So try to be consistent with that notation. Let's see, we got 1 here. 1 plus 1 is 2 squared. 1 minus 3 is negative 2 squared. Multiply that stuff out. We'll have 4 times 4, 16a. And we want that to equal negative 48. So set that equal to negative 48. Divide both sides by 16. It looks like we get a equals negative 48 over 16 or negative 3. Solve for a. So a is negative 3. Plug that back in. And there's the desired polynomial function. It's degree 5, right? Right. It's a little bit of a story to see that. But here we've got degree 1. Here we've got degree 2 when you multiply out. And here we've got degree 2 when you multiply out. 2 plus 2 plus 1. Yeah, it's degree 5. What's the leading coefficient? Can you tell? Yeah, it's going to be negative 3. If we had coefficients inside here of the x's, that would make it a little more complicated, but we don't. The leading coefficient is negative 3. Can you tell the constant term? Maybe. Well, we have to square this stuff out to get the constant term. There's a trick. There is no constant term. Every term is going to have a factor of x in it. So there'll be a power of x. There is no constant term, it turns out in this. Were they to ask us something like that? Constant term is 0. That's what we have here. So same idea as the previous examples, except we've introduced this multiplicity stuff. Okay, kind of shifting gears here to try to get to the graphing of these functions. We can get a fair to good idea of the graph of a polynomial function by finding the x-intercepts, that is the real zeros, and using a test value in each of the intervals that result from removing the zeros from the real line to determine if the function is positive or negative on these intervals. All right, that's a mouthful. Let's just illustrate it. So as we had, let me scroll back up to the picture we had earlier. Here, we're going to find these things here. So we're going to find the x-intercepts. We're going to list them in order. We're going to see before to the left of this first x-intercept, I know the function is either entirely below the x-axis or entirely above the x-axis if it's a polynomial function, because it's continuous. If it changes from positive to negative or negative to positive, it's got to cross the x-axis. And we're going to know everywhere that it crosses the x-axis. So we'll take a test value over here, plug it into the function and see if we get out a positive value or a negative value. If we get out a negative value, the function must be entirely negative over there. We get out a positive value, the function must be entirely positive over there. And similarly, between these two, and these two intercepts, and also to the right of the largest intercept. So stepwise, first we'd find the black points. Next, we'd take test values and see if the curve is above or below the x-axis by seeing if the output is positive or negative from the function on those little intervals. That's what this note's trying to say. Let's illustrate it. Okay, consider f of x equals 2x squared times x minus 4. Part A, list each real zero and its multiplicity. Determine whether the graph crosses or touches the x-axis at each intercept. Okay, part A, you want the zeros. We need to factor it. It's already factored. How convenient. So we'll set each of the factors equal to 0. So we'll set this x squared factor equal to 0, and we find x equals 0 is a 0 or root. It's of multiplicity 2 because that factor of x is to the second power. 4 is also a 0 or root. It's of multiplicity 1 because we're dealing with a factor x minus 4 to the first power. So only 2 real zeros. That means only 2 x-intercepts. To find the x-intercepts as points, we'll set y equals f of x equals 2x squared times x minus 4. Set the function equal to 0. We've dealt with that upstairs. We find x equals 0 and y equals 0 because they're x-intercepts, and x equals 4. Expressing them, I guess, not as points, but simply as x values. Of course, the corresponding y value is 0. They're x-intercepts. Now, what the previous note said is, let's take the whole real number line and break it into intervals using the x-intercepts. So we're going to start at negative infinity and go all the way to infinity, if that made any sense. And we're going to remove 0 and 4. List the x-intercepts in increasing order as they appear along the real number line. We've really taken the real number line and removed 0 and 4. Remove the x-intercepts. So you broke it in 2 places, producing 3 pieces. These 3 open intervals. These are all the x-intercepts. So, since we're dealing with a polynomial function, a continuous function, this function must be positive throughout this first interval or negative throughout this first interval. It must be positive throughout this second interval or negative throughout this second interval, and similarly for the third interval. So which is it? I mean, it could be positive in all 3 of them. It could be positive, negative, positive. It could be negative, negative, negative. It could be negative, negative, positive. Let's do a sign test. So what we're going to do is pick a number, any number in this interval, and plug it into the function. If the function is positive at that number, it's positive throughout this interval. If the function is negative at that number, then the function is negative throughout this interval because it has the same sign at all points of this interval, and similarly for the other intervals. So plan is, look at the interval, take a test value, plug that test value into the function, and look at the sign of that test value. And that tells you above or below the x-axis. First interval, negative infinity to 0. What's your favorite number in that interval? You're going to have to do arithmetic with it. Can you use 0? No, it's an open interval. 0 is not an element of this interval. If it was, I'd use it because that's the world's easiest arithmetic. You may choose any number you like from this interval. Well, save yourself the stress and choose smaller numbers. So let's choose -1. That's in this interval. We'll plug -1 into the function. So putting -1 into the function and calculating f of -1. Call the test value c. We're computing f of c in this row in the table. If I'll plug -1 in, we'll get a -1 there. That'll be 2 times 1 times, let's see, -1 minus 1 would be -5 times 2 would produce a -10. Plug -1 into the function, get -10 out. So at this point in the interval negative infinity to 0, the function is negative. Well, it must be negative throughout that interval. That is, the graph must be below the x-axis throughout that interval. Because it's below the x-axis at this one point, we got a negative value out. Pick a number, any number between 0 and 4. Yeah, arithmetic with small numbers is easier. You use 1 or 2. Can't use 0 or 4 because they're endpoints. And this is an open interval. Doesn't include its endpoints. So we'll use 1, do the arithmetic. Trust me on this. We get -6 out there. Negative, so the function is below the x-axis throughout that interval. So it's below the x-axis, and then it's below the x-axis again. Hey, what happened at 0? It must have touched the x-axis and not crossed it, because it didn't change sign. It stayed below the x-axis and below the x-axis. The next interval, 4 to infinity. Pick your favorite number, pick a small one, pick 5. Plug it into the function. Looks like we get 50 out, positive 50. It's a plus that matters. You get a positive value out at that point, then you're going to get positive values out at all the points in that interval, because the graph must be above the x-axis on that interval. Points on the graph, we took x values and we got f of x values out. So we get the point -1, -10. We get the point 1, -6. We get the point 5, 50. The book lays it out like this. That's a pretty big number. We might have trouble getting these all to fit on a graph, but we'll talk about that as well shortly. So what's up with part B? Determine whether the graph crosses or touches the x-axis at each x-intercept. So we found the x-intercepts of 0 and 4 in part A. Since the graph does not change signs at 0, by which I mean read from left to right, it's below the x-axis and remains below the x-axis. Better yet, it's negative and it remains negative. Then it didn't cross the x-axis. It must have touched it. But it does change sign from negative to positive. It goes from below the x-axis to above the x-axis at x equals 4. Well, it must have crossed the x-axis then at x equals 4, because it went from below the x-axis to above the x-axis. I actually prefer to describe these in terms of signs. It went from being a negative function to a positive function as x transitioned from this interval to the next interval, because the graph must have crossed the x-axis. Let's talk about some more stuff. Now, you want a graph of this, right? This verbal description of touching the axis and crossing the axis. You're drawing pictures in your head, one would hope, to try to envision what that really means. So we'll come back. We're not done with this one. But let's introduce a little more observations, and we'll come back and explore that function some more. We see from the previous example that if r is a 0 of even multiplicity of a polynomial function f, then f does not change sign from one side of r to the other. What we had in that previous example was from the x to the second power, 2 is even. From that factor, we had the 0, the root of x equals 0, that first intercept. And the function, it didn't change sign. It remained negative. The graph remained below the x-axis, whether we were to the left or the right-hand side of 0. The reason that happened is that factor didn't change sign when we went from one side to the other. You plug numbers less than 0 in or numbers greater than 0, this is going to be positive. This factor will be positive away from 0. So it doesn't change sign. This factor doesn't change sign. And that's because, looking for the word even, change sign one side or the other. There it is. And that's because the exponent is even. That is, when we use the terminology that the graph of f touches the x-axis, that occurs when you have these even exponents. I don't know if it was above and came down and touched or below and came down and touched, but I know that even exponent, you're not going to get a change in sign from one side of the 0 to the other side of the 0 that corresponds to that factor. So either the curve goes up and touches the x-axis and then goes back down, or comes down and touches the x-axis and goes back up. Touches is a bit ambiguous. All I know is it didn't change sign. Maybe it was negative on both sides, maybe it was positive on both sides. The even exponent or even multiplicity simply tells you it didn't change sign when you went through that zero. If r is a zero of odd multiplicity in the polynomial function, then f changes sign from one side to the other. So this factor is raised to the first power, but if I put in a number a little bit bigger than 4, this is going to be positive. If I put in a number a little bit less than 4, this number is going to be negative. If it was raised to an odd power, those sign claims still hold. So on one side of 4, that is for x slightly less than 4 versus x slightly greater than 4, this factor has different signs. You raise it to an odd power, it's still got different signs on the left or the right of 4. So when you have a factor of odd multiplicity, that's when f changes sign from one side to the other. Or in the terminology we've used, that's when f crosses the x-axis. So you can tell the difference between touches the x-axis and crosses the x-axis based on evenness or oddness of the multiplicity of the zero at which you have the x-intercept. Even exponents, touches. Odd exponents, crosses. So we're getting a lot of mileage out of just some algebraic properties. Another definition before we go back and look at that same example again. The points at which a graph changes direction from increasing to decreasing or from decreasing to increasing are called turning points. Each turning point yields either a local maximum or a local minimum. All right. We don't have a way of finding where these turning points is. One of the biggest applications of Calculus 1 will be to find where these turning points are, to find where local maxes and local mins are that we've mentioned already in the past. For us, we'll be able to tell a little bit about how many turning points there are based on the x-intercepts. As given in the following theorem, which we don't have the technology to prove, we'll take it as given, requires some knowledge of Calculus 1 and also requires some knowledge of the fundamental theorem of algebra. So theorem 4.1.a says, if f is a polynomial function of degree n, then the graph of f has at most n-1 turning points. If the graph of a polynomial function f has n-1 turning points, then the degree of f is at least n. So the number of turning points is related to the degree by a subtraction of 1 from the degree. There's some at most and at least comments in this as well. Yeah, that's in some sense that's related to multiplicities of zeros of something or other, some polynomial. But what this tells you, for one thing, as we'll see when we look at pictures, if there's a bunch of turning points, then this curve must be really wiggly. It goes up and it comes down, it goes up and it comes down, it goes up. So it wiggles a bunch if it has a lot of turning points. If n is big, then it's going to potentially have a lot of turning points. So when you see a wiggly graph, if it's a polynomial function, it must be a high degree polynomial because it wiggles a bunch. Let me say that one more time. You get the graph of a polynomial function. If it wiggles a bunch, if it's got a bunch of turning points, or turned from increasing to decreasing, then it represents a high degree polynomial. If it had, say, 10 turning points, then it must be degree at least 11. Now there's some at least and at most statements there. I can't say if it doesn't wiggle much, then it has to be low degree. That's not true. As we saw maybe in some of the powers of x, where n was even. We looked at x to the 8th, it only had 1 turning point. That's exactly what this says. It's encompassed in the at least n and at most number of turning points. But if it's wiggly, that is, if it has a lot of turning points, then it must be somewhat high degree, and we can quantify that, is what theorem 4.1.a says. The behavior of the graph of a function for large values of x, positive or negative, large and absolute value, is referred to as its end behavior. This type of thing you will explore in calculus, a bit less than the maximum and minimum stuff, but this end behavior will come up in calculus as well, not prominently, but it'll be in there. Theorem 4.1.b about end behavior says, for large values of x, either positive or negative, the graph of the polynomial function f of x equals a to the n, x to the n, and so forth. A sub n is non-zero. Resembles the graph of the power function y equals a to the n, x to the n, for large values of x, either positive or negative. So what that means is when x is really big, this function, it's dominated by that first term. That's the end behavior. So this first term dominates, which makes sense. If x is large values, if x takes on large values, x to the n is going to be a lot bigger than all these other powers of x. So that's pretty informal, but here's what we're taking. If you'd like, we can even take this as a definition. Y equals a to the n, x to the n is the end behavior of this function. F of x equals a sub n, x to the n plus the other stuff. So finding end behaviors is pretty easy. All you got to do is find the leading term. As an example, consider, well, that's that function we were working on previously. So back to the supplements, this function again, f of x equals 2x squared times x minus 4, continuing, part C. Determine the maximum number of turning points of the graph, part D. Determine the end behavior, that is, find the power function that the graph of f resembles for large values of the absolute value of x. We're just looking for the leading term in part D. Okay, maximum number of turning points. Well, if we multiply this out, you can see it's a third degree polynomial, n equals 3. How many turning points can an n degree polynomial have? At most n minus 1. So this has at most 2 turning points. That doesn't mean it's got 2 turning points. It could have less than 2 turning points. And it very much depends on the coefficients. It's a bit of a long story. We do know the intercepts, and we will be able to graph it in this particular case. So we'll be able to see specifically how many turning points there are. Part D, they say determine the end behavior, that is, find the power function that the graph of f resembles for large values of x. Easy enough, that's just the leading term. So the end behavior is given by this. Actually, maybe we don't graph this one. I think we're going to graph something else. We'll keep an eye on turning points. We have 2 intercepts. And if I was to guess 2 intercepts, I think this has, I think it'll have exactly 2 turning points. Actually, I can't really explain that without graphing it. We got the equipment to graph it now. We're just going to illustrate graphing with something different. Returning to the notes, let's do, let's look at a couple of other examples, and then we'll plow into graphing. Okay. So here they've given us a graph. They say, construct a polynomial function that might have the given graph. More than one answer may be possible. Yeah, right, because we won't know the leading coefficient, for example. If they gave us a point on the graph, we might be able to tie it down a little more. But the point of this exercise is, you know, the x-intercepts, they gave them as black points on the curve. And you know where this graph crosses the x-axis and where it touches the x-axis. It crosses here and here and touches in the middle. That tells you something about multiplicities of the x-intercepts as roots of the polynomial function. X-intercepts or zeros are x equals 0, x equals 1, x equals 2. These three x values give x-intercepts. They have corresponding factors respectively. X minus 0, or simply x, x minus 1, and x minus 2. So those must be factors. By note 4.1.c, where we looked at the multiplicity stuff, since a graph of f crosses the x-axis here and here at intercept x equals 0 and intercept x equals 2, then those two factors must be of odd multiplicity. The function changes sign from positive to negative here and changes sign from negative to positive here. Goes from above the x-axis to below it. Here it goes from below the x-axis to above it. When that happens, the multiplicity of this 0 of that polynomial function must be odd. Odd multiplicity. What's your favorite odd non-negative number? Non-negative integer is probably 1. So we could take 1 as the factor, but we don't know. It could be anything odd. So we must have the factors x and x minus 2, the factors associated with these two intercepts, to be of odd multiplicity. Since the graph only touches the x-axis at x equals 1, then the factor x minus 1 must be of even multiplicity. So we might have something of the form x times x minus 1 squared times x minus 2. Notice the x and the x minus 2, those two factors are of odd degree. The exponent on them is odd, it's 1 in both cases. So we've done this in a minimalist way. And x minus 1 associated with root 1, where the graph touched the x-axis, that has an even exponent. So here's a candidate. I'm a little worried whether we ought to have a positive or a negative coefficient. So it said consider this function. If we were to multiply this out, we'd have an x to the 4th as a leading term. So the end behavior would be x to the 4th. What does x to the 4th look like? A big opening upward. Things similar to a y equals x squared. It has some subtle differences. It's not parabolic, but it opens upwards. And we put in big X values and we get out big X values, just like this one. Big positive X values, big positive Y values. In that X to the 4th function, you put out big negative X values, large absolute value. You get out big positive values. And this function behaves in the same way. Since this is the end behavior, we do get out big positive things when the absolute value of X is large, positive for absolute value of X large. This function works. This is the simplest function that we could choose as a solution to this. If we took this given graph and reflected it about the x-axis, it'd still have the same crossing behavior and touching behavior of the x-axis, but it would be then negative, right? These values would be below the x-axis. These values over here would yield below the x-axis if we took a mirror image, a reflection about the x-axis, and that would change some of the other behavior. So that's why we had to explore the end behavior. But we found a function that matches that graph. Dot, dot, dot. So I don't want to end the example there. It said more than one answer is possible. All right. One thing we could do is multiply by a constant up front and have some positive multiple of this function. You multiply by a positive value, for all I know, you get the same kind of thing. I have no clue what y values are except at those three intercepts. Also, all you know about x is it has an odd exponent on it. All you know about x minus 2 is it has an odd exponent on it. All you know about x minus 1 is it has an even exponent on it. We chose the smallest numbers we could use that were even and odd. But You know, we could have chosen differently. We could have chosen 3 and 3 as the odd exponents and 4 as the even exponent. This would work as the end behavior model of y equals x to the 10, which goes up when the absolute value of x is positive. Gives out, absolute value of x is large. It gives out positive values. So this one matches the curve as well. It didn't give us a lot of information in that little graph. Lots and lots and lots of choices here. We could have taken 10 times what we chose, or 10,000 times what we originally chose. I don't know why values. We could have chosen any mixture of even and odd as appropriate. We could have taken 15 on the x factor, that's odd, 7 on the x minus 2 factor, that's odd, 20 on the x minus 1 factor, that's even, and so forth. So lots and lots of potential choices on what the function could be. But we chose the natural choice on the previous slide, the most elementary choice. Construct a polynomial function that might have the given graph. More than one answer is possible. Same idea as before. They did give us a point on this one, so that might allow us to tie it down a little bit more solidly. Intercepts. Okay, they've calibrated this in a funny way. Each of the little tick marks represents 1/2 unit. Notice here we have a half, 1, 1.5, 2. So they've calibrated the x-axis by halves, calibrated the y-axis by what? 1, 2, 3, 4. 3. Looks like each tick mark represents 3. Anyhow, I need the x-intercepts. So I definitely need to know the calibration on the x-axis. We've got an x-intercept here. This is x equals -3, right? By the way, we've calibrated the axes. Here's an intercept at -1, an intercept at 0, and another x-intercept at 2. So we get -3, -1, 0, and 2 is the x-intercepts. So we know factors of this function. Must have factors of x minus -3, that is x plus 3, x minus -1, that is x plus 1, x minus 0, or just x itself, and x minus 2. So we get these 4 factors based on the x-intercepts. But sometimes it crosses the x-axis, and one time it touches the x-axis. So that's going to determine even and oddness of the exponents on these 4 factors. Crosses the x-axis at -3, -1, and 2, as observed. 0, 0, when x equals 0, it touched. But since it crosses at these 3 points, the corresponding factors must be of odd multiplicity, as we stated in note 4.1.c for the record. But it touches, the graph of f touches the x-axis as x equals 0. So the factor x, x minus 0, must be of even multiplicity. Again, note 4.1.c. How about this? We could take f of x equals, how about x plus 3 to the first power? That'll take care of the fact that it crossed the axis. Got an exponent of 1, didn't write it, but it's there, and it's odd. X plus 1, that corresponds to the x-intercept of -1, odd exponent, it's a 1. X squared, we wanted an even exponent on the factor x, favorite even number is 2. And we needed an odd exponent on x minus 2, as explains, we'll take a 1 there. So in terms of choices of exponents, these are the smallest choices we could have made. This will give an appropriate shape in terms of crossing or touching the x-axis. Let's put a coefficient out front. That could be anything. Doesn't affect the x-intercepts. So we'll take this as a leading coefficient. We'll need a to be greater than 0. So that then the end behavior, if you multiply all this stuff out, will give you ax to the 5th. What does ax to the 5th do when x is large in absolute value? On the positive side, it goes up, and on the negative side, it goes down. Positive side, it goes up. Negative side, it goes down. Yeah, that's why we need to take the leading coefficient to be positive. We take it negative and it goes up on the wrong side and down on the wrong side. But y equals x to the fifth, or ax to the fifth, where a is positive, goes up when x is a large positive value and down is negative when x is a large negative value, just like the graph of the function we're given. So we can first say that parameter a must be positive. Next, we knew that the graph passed through the point negative 216. That was given in the graph. Let's look at that real quick again. That was given information. It passes through the point negative 216. Again, up on the right, down on the left, negative over here, positive over here, more appropriately. F passes through that point, so we need, when x is negative 2, the function value to be negative 16. What is f of negative 2? We have a form of f, so we'll plug it in and see what we get. We need f of negative 2 to be a times, we'll plug negative 2 in there, and there. Got the parentheses around all the negative 2's. There's the x squared term, for example. Do the multiplication, careful with the negative signs, and that simplifies to 16 times a. And we wanted that to equal, 16. Oops, the typo there. We wanted it to equal 16. Error there, not negative 16. I will correct the notes as usual, always finding typos. We want f of negative 2 to equal 16, so we'll set that 16a equal to 16. Divide the 16 out, a must be 1. So we could take f of x to be x squared, x plus 3, x plus 1, x minus 2. This has the correct intercepts. It passes through that point. It crosses the x-axis where it's supposed to, and it touches the x-axis where it's supposed to. So there. But we could have made different choices for the exponents. For example, we could have chosen an exponent of 3 on x plus 3, as long as it's odd. Instead of 1, we could use an exponent of 3. Instead of 1 here, we could use an exponent of 3. Instead of 1 here, we could have used exponents of 3, for example. Instead of 2, we could have used 4. So you can change these exponents, maintain their parity, their evenness or their oddness, and we could have chose something else. But if you change those, then you got to go back and use this information that f of negative 2 equals positive 16. And then you've got to do the computation similar to what we did to find a new leading coefficient if you change the exponents. But here's an example of another function that will give the same behavior. This function has the correct intercepts and the correct touching and crossing of the x-axis. And if I've done the arithmetic correctly in choosing this leading coefficient, it passes through the point negative 2, positive 16 as well. So there's another possible function. I can't tell you which of these is correct unless you give me more information. If they'd have told us the degree of the polynomial, this one is degree what? 2, 3, 4, degree 5. This one is degree 2, 3 plus 3 plus 3, 11, I think it is. They both satisfy the information they gave us is the problem. So I can't give you a specific function unless you give me more information. So in summary, on grading, on graphing, note 4.1.d says, when we analyze the graph of a polynomial function as follows, determine the end behavior of the graph of the function. That's just the leading term. Find the x and y intercepts of the graph of the function. Easy enough, we've done that earlier. Determine the zeros of the function and their multiplicity. Okay, that's going to involve factoring. So you have to be asked about polynomial functions you can actually factor. So you can't factor just anything. Nobody can. So it has to be literally a textbook example so that you can do the factoring and find the zeros. This multiplicity idea is a new one that's popped up in this section. Determine the maximum number of turning points. Okay, we can do that using the degree of the polynomial function. and then use all that information to draw a complete graph of the function to help establish the y-axis scale, find additional points on the graph on each side of any x-intercept. Okay, let's do them 5 steps in the following example. So here's where we'll finally create a graph. Analyzes polynomial function. 5th degree polynomial. Let's follow those steps as laid out. So we'll just recall each of the steps. We know what to do. First step was determine the end behavior of the graph of the function. Well, that's just this first term. So y equals negative x to the 5th is the end behavior of the graph. This tells us about the function maybe where it's positive and where it's negative when x is a big number in absolute value. More of that when we look at the graph. Part 2, find the x and y intercepts of the graph of the function. First, let's find the x-intercepts by setting the function equal to 0. That's going to require us to factor the function. Okay, so here's arguably a tricky part. Factor this. See any common terms? X squared. Say negative x squared. Factor a negative x squared out. That'll leave a positive x cubed here, a negative 5x squared here, a negative 4x here, and a positive 20 here, which is hopefully exactly, I said the correct thing, what we have here. So factor the easy stuff out first. This one's a little grouping trick. The ratio of the coefficients here are 1 to negative 5. You know what? The ratio of the coefficients here is also 1 to negative 5. So we can group these. Let's factor an x squared out of this first one. Factor an x squared from these two will leave you with an x minus 5. Factor an x squared out leaves you with an x minus 5. And these two, let's factor out a negative 4. Factor the negative 4 out will leave you with x minus 5 as well. So we get a common x minus 5. This is literally a textbook example because it factors by grouping. Now let's take that x minus 5 and factor it out from here and here. Bad place for a new line. That's what I got from the software. Factor that x minus 5 out. Leaves you with the negative x squared out front. The x squared is right here, and the minus 4 is right here. Factors down to this. Can you factor it more? Yeah. X squared minus 4, difference of two perfect squares, factors into x minus 2 times x plus 2. So here is that function completely factored. By the way, multiplicity 2, multiplicity 1, 1, 1. So in the future, that'll tell us about touching the x-axis versus crossing the x-axis. Looks like it crosses the x-axis 3 times, touches it once. We're in the midst of looking for x-intercept, so we'll set that function equal to 0. Solve for x. Set y equals f of x equals to 0. Solve for x, and we get x equals negative 2 from this factor. X equals 0 from this factor, x equals 2 from this factor, and x equals 5 from that factor. I've listed them in order down here as they would appear along the real number line, left to right, least to greater, not the order in which they appeared in the product. So that's why I had to jump around to match these up. This is essential because we're going to create some intervals out of these x values and do some things with test values as they indicated. For the y-intercepts, that's easy. We'll set x equal to 0, plug 0 into the function, you get 0 out. Right? There's x's everywhere. So you get 0 out of that. So the y-intercept is also 0. Passes through the origin. That's what you got from that. So that takes care of the first 2 steps. Determine the zeros of the function and their multiplicity. Okay. 0 is a 0 of multiplicity 2, a root of multiplicity 2 because of the power of 2. The rest of them, because the exponent is 1 on those factors, The other zeros, -2 from this factor, 2 from this factor, and 5 from that factor. These are each of multiplicity 1. Exponents of 1, 1, 1, multiplicity of 1, exponent of 2, multiplicity 2. Determine the maximum number of turning points on the graph of the function. Okay, it's a 5th degree polynomial. We multiplied it out on the previous slide. N equals 5. The maximum number, by theorem 4.1.a, of turning points is n minus 1. So it could have at most n minus 1 equals 4 turning points. We'll graph it and we'll count turning points. All right, we're going to draw it. They want us to plot a few points. Okay, let's plot some points maybe between some of the x-intercepts. The x-intercepts were -2, 0, 2, and 5, listed in order. Let's take -3. It's less than -2. Trust me on the arithmetic here, it's a bit messy. We get 360 out at -3. So that gives us a point on the graph. Let's plug in -1, right? -2 is where we'll have a x-intercept. So let's plug in -1. Trust my arithmetic, we get -18 out from that. So the point -1, -18 is on the graph. Let's plug in 1. We know what happens at 0. X equals 0 was a 0. X equals 1, let's plug that in. It looks like we get -12 out. Hey, it went from -18 to -12 when we went from x equals -1 to x equals +1. We went past 0. That's where it touched the x-axis. So I'm not surprised we get negative followed by negative. It's remained below the x-axis and below the x-axis. 2 is an intercept, so let's plug in x equals 3. Plugging in x equals 3, looks like it gives out 90. So that's a point on the graph as well. So let's graph that stuff. Okay, we know -2, 0, 2, and 5 were intercepts. We know the graph crossed here, and crossed here, crossed the x-axis, and touched the x-axis here. With the information I just stated, I don't know that it doesn't come down, cross, go up and touch, go down, go up and cross, come down and cross and go below. I don't know that without a little additional information. That's why we had those other points. We plugged in, because we plugged in 1 and got out -18. There's that point. -1, -18. We plugged in +1 and got out, I don't remember what we got out, negative something or other. Let's go back and look. Plugged in +1, we got out -12. So there's that point. We plugged in 3 and got out 90. I think we plugged in -3 and got out 360. So that's off the scale for this one, so we'll ignore that point. But since we've got these 2 points, these 3 points, other than the intercept, the graph must. We know it crosses. We know it's below the x-axis here. We know it's below the x-axis here, putting the negative outputs. So it must have been positive and crossed over to give negative below the x-axis, gone up and touched, remained below the x-axis, crossed, gone up here, passed through that point, and gone down. How many turning points did it have? At most 4. Well, it's turned here, goes down and turns over to increasing. It increased and turned over to decreasing. There's a second turning point. It went down and turned over and started increasing, decreasing followed by decreasing. It has a turning point here. And it went up, passed through this point. I don't know, it might have gone up, passed through this point, kept going up and then come back down. I don't know, I didn't plot that much detail, but it had to go up and turn around to come back down to intersect the x-axis again. That's 1, 2, 3, 4. So yeah, there's your 4 turning points, and we expected 4 turning points. Something we can extract from what we know is, well, how do you know it doesn't go, so we pass through this and wiggle around a whole bunch and then come back down? Well, if it wiggled around a whole bunch, it'd have more turning points, and we know it's only got 4 turning points. So that's this close to knowing some calculus type behaviors that we can extract from the fact that we're considering polynomial functions. And we know how many turning points a fifth degree polynomial function can have. How do you know it doesn't wiggle around more? Because I know how many turning points it has. And this is all related to something you will address in Calculus 1 and have some pretty solid equipment to address these ideas again in Calculus 1. You will have the technology in Calculus 1 to decide where is that little turning point down here and over here and up here. That I don't know. I don't know how to find where the turning points are. That's something you'll learn in Calculus 1. So that takes care of this section. Well, parting comment, read the book. It costs enough. There's some neat worked examples in the book. Examples 6, 9, and 10 from this section are worth looking at. They'll analyze them similar to the way we analyzed this number 114. So have a nice day. We've got polynomial functions introduced. I believe rational functions are next. We'll graph rational functions. And this chapter, again, will conclude with the fundamental theorem of algebra. Must be pretty basic stuff, pretty important stuff, because this is a class on algebra. So have a nice day. I will see you in section 4.2.